Okay, let's talk a little bit about the pH of salt solutions, because there could be a non-neutral ion in the salt causing the solution of the salt to not be neutral. Salts formed from the neutralization of a strong acid and strong base. The aqueous solutions are neutral because both ions are neutral. If you take hydrochloric acid, a strong acid, plus sodium hydroxide, a strong base, you'll form a salt, sodium chloride, and water, where the sodium comes from the strong base. Remember we said the conjugate acids of strong bases are neutral, and the conjugate bases of strong acids are neutral, so I've put together two ions, so the salt is neutral. Now what if I've got a salt of a strong base and a weak acid? So now I've got acetic acid reacting with sodium hydroxide. So now the salt I form is sodium acetate, and then I form some water. Sodium is still a neutral ion, but now acetate is the conjugate base of a weak acid. Conjugate bases of weak acids are themselves weakly basic. So since sodium is neutral, that means then the salt would be basic. Then what if I got a weak base and a strong acid? So you got, say, something like HCl plus ammonia, which is a weak base, and I form ammonium chloride, which is our salt. Now chloride was from HCl, so that's still a neutral ion, but the ammonium ion is the conjugate acid of a weak base, and conjugate acids of weak bases are themselves acidic, so the ammonium chloride aqueous solution would be acidic. It gets a little bit more prickly if you pick two weak things. You really have to look at the relative Ka and Kb. Where for the first three cases, we just to get an acidic, basic, or neutral, we didn't really have to look at the numbers. If we needed the precise pH, certainly, but I didn't really need to look at the Ka and Kb values. You really do if you've got two ions that are not neutral, though, because you got to see which one's going to dominate. So if I were to react acetic acid and ammonia, I would get ammonium acetate and water. Now, we already said that the ammonium ion was somewhat acidic and the acetate ion was somewhat basic. So which way is it going to end up? Turns out in this case, the Ka and the Kb are equal, and so that salt would end up being neutral in that case. But if the Ka were bigger, it would be acidic. If the Kb were bigger, it would be basic. So let's look at these salts and determine whether they're acidic, basic, or neutral. Potassium nitrate. Potassium nitrate, the potassium comes from potassium hydroxide, which is a strong base. Nitrate comes from nitric acid, which we just said was a strong acid. And so that salt would be neutral. Iron nitrate. Again, nitrate comes from nitric acid, which is a strong acid. Iron is a transition metal, though, and it's a +3. Highly charged ions, in particular transition metal ions, tend to be weakly acidic. And that's somewhat of a little case we'll talk about later. But if you see a transition metal atom, particularly one that's +3, you should start thinking weakly acidic. And so we'll say that one is acidic based on that. And if you say, well, what hydroxide is it based on? It's based on iron hydroxide. That's not on your strong base list, so you should still get it right that the iron is weakly acidic. NaC6H5O. You've got that compound. Now you got to say, well, sodium is neutral, as we've been mentioning, but the C6H5O, there might be a couple of different anions with that formula. So how do I even know? Is it on the strong acid list? This is why it's important that you go back and review your strong acids and your strong bases. Whatever that acid is, we know that it would be weak. So then that ion must be weakly basic, and I would end up with a basic salt, even if you don't know what that anion is. In the case if you have something organic like that that you couldn't name, I would tell you what it is in the KB or Ka for the conjugate acid, so you'd be able to solve the problem. So if we look at the last one, we got ammonium formate. And so we got the Kb for the formate and the Ka for the ammonium. It looks like the Ka for the ammonium is a little bit bigger by an order of magnitude, looks like, or power of 10. So it looks like that solution would be weakly acidic because of the net effect. So let's say we've got a 0.1 molar solution of sodium hypochlorite. We're not really worried about the sodium. We're worried about the hypochlorite ion because that's the non-neutral one. And we've got a Ka for the hypochlorous acid, which is what you'd be able to find in the table at the back of your book at 3.5 times 10 to the negative 8th for our hypochlorous acid. We want the pH of that solution. So we're going to have to work a little bit on that. So I transferred the information over. The reaction we're looking at is the hypochlorite ion reacting with water, because sodium's neutral, to produce hypochlorous acid plus hydroxide. But that's going to have a Kb, not a Ka. And what you're going to find for a lot of these anions of weak acids is that the weak acids in a table, but they didn't give you the Kb's or all the conjugate bases. So we're going to get it using our Ka-Kb relationship that we talked about in a previous video. So Kb is going to equal 1.0 times 10 to the negative 14th divided by the Ka that we were given, 3.5 times 10 to the negative 8th. We're going to run that through our calculator. And you're going to get 2.9, we'll say, times 10 to the negative 7th. So now we got a workable Kb. We said we had a 0.1 molar solution of that. So concentration of the OCl minus. Water we're going to ignore. OCl OH. And why are we excluding the water? It doesn't impact the equilibrium constant expressions. So we're going to have initial, we're going to have change, we're going to have equilibrium. And that is what we're going to set to 0.10 molar. None of that, none of that. But I am going to need an equilibrium constant expression for this. So our Kb now is going to equal concentration HOCl, concentration of hydroxide, which is what we're interested in if we want the pH, over concentration of OCl minus. So this, I'm going to lose some, and I'm going to gain some of the two products. So that'll be x. This will be 0.10 minus x. But with the Kb that smaller, approximation is going to be in full effect. And so we're going to say that's about equal to 0.1 molar, which will allow us to make our simplifying approximation. So essentially we're going to plug and chug, and we'll say x squared divided by 0.10 equals 2.9 times 10 to the negative 7th. So x squared equals 2.9 times 10 to the negative 8th. Then we have to square root that. So we're going to run that through our calculator. And so that will give us 5.3 times 10 to the negative 4th molar. Now that X is equal to the concentration of the hydroxide ion and the hypochlorous acid concentration, where we're going to assume the HOCl is roughly unchanged, which it would be with those sig figs. So what we can calculate then is the POH is going to be negative log of 5.3 times 10 to the negative fourth power. So we're going to negative log that. And we get a POH of 3.3. But the problem asks for the pH of this solution. So pH is 14 minus 3.3. So 14 minus 3.3 is going to give us, what, 10.7, which would be the answer we are looking for. And so that would have a relatively high pH because that's a weak base. That's the conjugate base of the weak acid, hypochlorous acid.